Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the lecture number 21 of the SwayamPrabha course titled Maritime Structures, Types, Construction, Pre-Service Analysis and Design, offered by Department of Maritime Engineering at IIT Gandhinagar. Friends, this is a profession-enabled course where the employment opportunities in the maritime sector are increasing with a very good capacity build-up in this sector. So, the lectures what we are proposing in this is of multidiscipline in order. So, I want you to follow them very carefully and also read the reference materials in parallel. Maritime engineering sector is a multidisciplinary entry with different branches of engineering as civil, mechanical, electrical, electronics, aeronautics, naval architecture, structures, offshore engineering and so on. Therefore, friends, the topics covered in this course will cater to the basic requirements of all these engineering discipline graduate students and the listeners, so that the high-end complexity of mathematics involved in maritime engineering sector is tried to be addressed in a very simple manner, so that one can easily follow without much difficulties. However, friends, the content of the lecture in terms of its derivation, applied examples will be of an order of very high quality. Therefore, you need to read some supplementary materials to also learn them in parallel. With this context, now let us look into the lecture number 21, where we are going to discuss about design of an element for lateral torsional buckling, which is briefly called as LTB. Friends, the design for bending and flexure is a very simple phenomena and very simple mechanism involved in structural design of steel structures, especially familiar with civil and structural engineering students. However, for mechanical, electrical, electronics and other multidisciplinary sectors, this design examples may be slightly complicated because the background information on deriving these design equations are not presented in this course. So, however, I will try to make it as simple as possible so that the equations are borrowed from the international codes. We will tell you the basics how these equations are landed up, then we will use these equations to illustrate design examples so that you are comfortable to understand the phenomena, the fundamental behavior of a member under LTB, but however, the mechanical or mechanics background in understanding LTB from fundamental principles is not a part of this explanation of this course in this lecture. So, you require certainly additional reading materials which can be always taken away from the list of references given under the course web page of this course on maritime structures. So, friends, take you into the classroom of lecture number 21, where we will discuss about lateral torsional buckling. So, let us try to understand first the difference between the flexural buckling and torsional buckling. First, let us understand what is buckling. So, let us go back. Buckling is closely related to a geometric parameter. It is not a load control phenomena, friends. What I mean to say, if the cross section is very thin and slender, even under very small magnitude of load, it can buckle. So, buckling essentially is a geometric parameter. However, buckling cannot happen if you do not have an axial load, that is agreed. So, there has got to be some load of magnitude, but buckling essentially is a form dominant characteristic of a structural member. So, when a buckling occurs when the section is declared as slender. We all heard about something called slenderness ratio. Okay, it is a dimensionless number, it is a simple number. So, if this ratio is less than or equal to 12, then buckling is not predominant. When it increases, then buckling plays a role. Therefore, many of the international codes classify structural members as slender and short members. Essentially, if you look at the literature, this is more or less associated with compression members like columns. But here we are talking about torsional buckling in beams. So, when a beam can buckle, then what is the difference between buckling and bending, or flexural buckling, what we call as bending? So, flexural buckling can occur in any compression member, okay, whereas torsional buckling can occur even in beams. So, flexural buckling can occur in any compression member which undergoes deflection arising from bending. Let us take a very simple illustration. Let us say an I-beam is used as a column member. Okay, let us try to draw this I-beam in a three-dimensional perspective. Let us say a column member like this. So, this is my cross section property of the member. I hash the member. Okay. Now, let us say I have a floor here. So, this dimension is expected to be the unsupported length, which we call height of the column. Now, this cross section has got two axes. This is one axis, I call this is axis 1 1. There is another axis to this, which is axis 2 2. Both axes are passing through the CG. So, I can say 1 1 and 2 2 are geometric or centroidal axis. Okay. Now, if you look at the moment of inertia of this cross section about axis 1 1 and about axis 2 2, you will notice from simple calculation that the moment of inertia of this cross section about axis 1 1 is higher than about 2 2. Okay. So, the axis about which the moment of inertia is maximum is generally called as major axis, and the one which is lesser is called the minor axis. They are not principal axis, they are centroidal axis, they are geometric axis. Okay? They are not principal axis. Major and minor. Major refers to higher moment of inertia, minor refers to lesser moment of inertia. So, moment of inertia about the axis 1 1 is much higher in this cross section compared to 2 2. I can call this as a major axis. Okay. Now, let me try to work out something called slenderness ratio. We call this as lambda, which is L by R minimum. Okay, where L is the unsupported length on any plane of reference, whereas R is radius of gyration, and radius of gyration is given by square root of I by A. Now, friends, since this cross section has got two moments of inertia, that is I 1 1 and I 2 2, therefore, I should say it will also have two radius of gyration R 1 1 and R 2 2, correct? Area of cross section will be same. So, area of cross section will not matter, but based on the value of I substituted in this equation, R will have two values. So, since I 1 1 is higher than I 2 2, can you expect that R 1 1 will be higher than R 2 2? Is it not? Because I 1 1 is higher. So, the moment of inertia I 1 1 is higher, therefore, radius of gyration will become higher. Therefore, if I say I want to use the minimum radius of gyration, then I would use R 2 2 in this expression. Okay. So, given section I can compute radius of gyration which is minimum. Okay. So, then I can find slenderness ratio, the worst at which this happens. So, if this ratio is computed, then this ratio helps me to check whether this member will buckle. Please understand, I am not talking about bending, I am talking about buckling. So, buckling is a phenomena which happens on compression members under axial compressive load. The column will buckle. Okay? The column will, for example, if this is my column, the column, if this is my column, the column will buckle. Okay, it will get a lateral deflection along its height. We call this as buckling. Now, this is for a compression member. Now, let us imagine this for a beam. Okay, that is the lateral torsional buckling. So, let us talk about that and say the flexural buckling can occur in any compression member which undergoes lateral deflection causing bending. Two factors influence this. One is the slenderness ratio. So, when you can have large slenderness ratio, can have large slenderness ratio when R is minimum, correct? Because L is saying when R is minimum, then you can have large slenderness ratio. So, the slenderness ratio value is more or less governed by the cross sectional properties like moment of inertia and area of cross section, correct? It also depends on the unsupported length of the column member. Considering that in both planes 1, 1 and 2, 2, in both planes 1, 1 and 2, 2, the unsupported length remains same, then it is governed by the moment of inertia of the cross section and area of cross section and the plane about which you are considering or computing moment of inertia. So, now if you have a section which has got large slenderness ratio and least radius of gyration, this will govern the flexural buckling. Then when torsion comes into play, torsional buckling will occur in slender compression members. First of all, to initiate torsional buckling, the member has got to be slender. How will you check slenderness ratio? I have already given you the equation. So, identify the member, ascertain that this member is slender, then you can look for torsional buckling. So, therefore, friends, torsional buckling is one step advanced of flexural buckling, correct? One step ahead. So, torsional buckling can occur in slender compression members only which has got double symmetric shape. That is very interesting, friends. What do you mean by double symmetric shape? If I have a section with, okay, these are flanges and this is web. Let us have a section with deep web and equal flanges, option 1. Then the next option is comparable flange dimension and web depth are comparable by a ratio. I am not saying they are equal, comparable by a ratio. We will come to this ratio later. Okay? So, comparable by a ratio, right. So, in that situation, you can expect torsional buckling to happen. Now, the question is, where is lateral? Torsional buckling is okay. Buckling is found because slenderness. Where is torsion coming into play? Look at this figure. There is a cantilever and the cross section is an I-beam. Okay. Now, the cantilever span is L. Now, when the cantilever bends, for example, I have a cantilever loaded. When the cantilever bends, okay, this is bending. This is happening on the same plane as the whiteboard, correct? This is the plane. But here, this is lateral buckling, correct? This is lateral. This is not happening on the same plane of the beam. It is happening in a plane normal to the beam, right? It is happening on this horizontal plane, on this plane, whereas the beam is on the vertical plane. So, there is a lateral bending happening. Remember, the load is not applied lateral, okay? The load is applied vertical only. The load is applied vertical, but the beam bends lateral also. Beam anyway bends this way, no doubt about it, because of the load. Beam will also bend lateral. When this can happen? There should be some conditions. when this can happen. First let us understand, can we visualize this? This can happen expectedly when the span is very large and when the depth of the beam is very large compared to its breadth. So, I have a large deep sections. So, when I have a deep section under this load, this web element becomes a column. Okay? When I have a deep section under the compressive load, this element starts acting like a column. Now, a column is a compression member which can bend, which can buckle, and buckling happens on the column member. There is a lateral bending also, and of course, there is a deflection happening. So, the deflection and lateral bending twists the cross section. Remember, the deflection and lateral bending twists the cross section, and of course, the cross section is deep, therefore, it buckles also. So, lateral torsional buckling. Lateral torsional buckling. Why torsional? The cross section originally vertical is now twisted. The cross section originally vertical is now twisted. So, twisting, torsion, lateral, bending, buckling. So, it has got all phenomena involved in this. Bending happens because of deflection, span. Lateral deflection happens because of the large span and deep web. Buckling happens because the compression component, which is the web component, acts like a column and that buckles. Okay. So, now look at both the axes as I explained earlier, axis 1 and axis 2. Okay, look at this axis 1 alone. Let us look at let's 1 1. Let us call this 1 1 axis alone, and in this axis the beam or the column bends. Let me mark it here. If this is my 1 1 axis, okay, see here the cross section bends. So, there is a lateral shift. So, it is outward bending, here it is inward bending. Okay. Here it is outward bending on this plane, and on this plane it is inward bending. So, at any point along the length of this or along the height of the column will have twisting experienced, is it not? Because one face is bending outside, other face bending inside along its height or along its width. So, this can expect some twisting, buckling because compression load, lateral and twisting. So, lateral torsional buckling. Okay. Then one can expect that whether the buckling will be more about 1 1 or about 2 2. Will it be more about 1 1 or about 2 2? So, if I have this as 1 1 and this as 2 2, you can expect that the buckling will be more about 1 1 or 2 2, because you know the radius of gyration is minimum about 2 2. Okay. For the same height of the column, then the buckling can happen more about 2 2 if it is a column member. Okay. If it is a beam, then the issue is different. Okay. So, friends, let us look at these figures. We are talking about lateral torsional buckling. So, we are talking about flexural buckling, which is only same neutral axis shifting. Torsional buckling is only twisting about its CG. Lateral torsional buckling, there is a twist and there is downward and lateral movement happening. Okay, that is why it is called lateral torsional buckling. Okay. So, flexural buckling, torsional buckling happening only about twisting about the CG, lateral torsional buckling. So, this twist is torsional and this shift is lateral, correct. Having said this, let us look at this figure and try to understand what are the displacements happening in the cross section when a beam undergoes lateral torsional buckling. Let us say I have a cross section of this order. Okay, I have marked the cross section. This is a simply supported beam, let us say. This is a simply supported beam, right? A simply supported beam. The span of the beam is so large, the web is so deep, therefore, the beam undergoes lateral deflection. The beam also twists about its CG axis, and since the web is very deep, it undergoes buckling. So, lateral torsional buckling. Okay. Having said this, let us look at this beam here with the nomenclature. Friends, though we are not looking into the entire derivation of LTB in detail, but the nomenclature is very important to understand the equations given in international design codes, okay, like Euro code, Indian code, etc. We are going to do an example using these codes now in this class. So, let us take a simply supported beam. Okay. The cross section of the beam is as shown here as an I section. The cross section axes are x axis and y. So, whereas z is normal to the board, so I call this as the longitudinal axis and I call these as cross sectional axis. Okay. So, if I look at this figure, if this is my longitudinal axis and if y remains the vertical axis as normal, and can I mark this or this as x axis? Okay. So, I can mark if this is my z axis, if this is my y axis, this becomes my x axis. So, x y is a cross sectional axis and z is a longitudinal axis. Okay. Now, this is the elevation of this beam viewed from here. So, these two are the flanges which are seen in yellow color and this web is seen in the grey color. Can you see that? Now, what I do, I take a section I take a section at a distance z from one end. I take a section at a distance from it. Okay. Now, the beam is expected to undergo lateral deflection. How this can happen? When the span of the beam is so large, subjected to vertical loads, the beam is under vertical loads only. Okay. The beam is not under axial load, the beam is only under vertical load. Under the vertical load, since the span is too large, the beam can undergo lateral deflection. See here, the beam can undergo a lateral deflection, right. So, let us say the beam is undergoing this plan, this is plan. So, what you see in the yellow color is the top flange, What you see or what you do not see in the bottom is the bottom flange. Okay. What you see in the dotted line here is the web. So, I can draw the view from here, I get this, correct? It is the top view. So, in the top, because of the huge span of the simply supported beam, the beam undergoes lateral deflection, friends. Okay. This deflection is measured in which axis? Which will be seen in which axis now? There are three axes here. Z is longitudinal axis, Y is the vertical axis. Y will give you deflection. If I have a load here, the beam bends. This is along Y. Okay. This is deflection, but this is lateral. So, can you expect this lateral to happen along x axis? If this is my positive x, okay, it is happening this way in the figure. Therefore, I am saying the beam has moved its CG axis from this position to this position, and I call the lateral displacement as minus u. Why? Because this is my positive x. So, if this is z, this is y, and this becomes my positive x, the beam is deflected this way, so it is minus u. Okay. If this is positive y, the beam has gone down because of deflection, so minus v. So, now I am saying the coordinates of the displacements after deformation are minus u and minus v. Minus u is along x axis in the opposite direction, minus v is along y axis in the opposite direction, x y are the cross sectional axis, and z is the longitudinal axis. Are we clear about this, friends? Okay. Once I deform the beam under lateral deflection, the beam has twisted about some axis, okay, about some point. We call that angle as phi. Okay. Now, I want to give a new name to the cross sectional axis now. Initially, the cross sectional axis were x and y. Okay. So, y has now become eta, x is now become a new different name. So, I can say this has become eta and this has become c. Okay. Z, okay, z axis. So, now I can say this is z axis and this is eta. So, let us relate. Z axis is related to x, eta is related to y. Can we say that? Is it not? Because y is vertical, eta is vertical. Z is cross section axis, so can I call this as z. So, z and eta are correspondingly y and x axis deformations or axis after deformation. Can I say that? Okay. Having said this, let us look at the simply supported beam as you see in the figure, subjected to some loading. This loading will induce moment. The moment is marked as m0. Please understand, friends, m0 is the moment about, can you tell me which axis? This moment is about which axis? There are three axes in this cross section. One is the z axis, other is the y axis, the other one is the z axis, x axis, right? So, can I say m0 is actually same as mx? Can I say that? Because it is acting about x axis, am I right? So, with this m0 or mx acting on the beam will now bend. This will cause deflection. Remember, I am saying the beam will bend causing deflection, am I right? Deflection is measured along y axis, correct? Now, let us look at the components of this moment. So, let us say x and y are originally the cross section axis. After twisting, this cross section is now going to change and that has become c and eta, am I right? This is c, okay, z you can say, okay, z. Okay. So, it has become now z and eta. So, we already said z is corresponding to x deformation or x axis and eta corresponds to y deformation or y axis, whereas z and eta are cross sectional axis after deformation, whereas x and y are cross sectional axis before deformation, and of course z is the longitudinal axis of the beam. Any confusion, friends? Is it clear? Okay. Let us look at the second figure here. Now, all along the length of the beam is anyway going to bend because of the load or because of the moment caused by this. Fine. Because of the span of the beam is so large, the beam is also experiencing lateral deflection. So, that lateral deflection will be seen in which axis or which plane, friends? Measured along which plane? There are three axes here, z, y and x. So, now the lateral deflection will be seen in which plane or which axis? Will be seen along x. So, let me mark this variation along x, which varies along z. Z is the longitudinal axis now, right? So, it is going to increase the lateral deflection. Okay. So, now we already know at any point, if I have an applied moment mx, I can resolve this. Okay, I can resolve this with c and zeta. I can resolve this with z and zeta, as you see here. Now, if this angle of shift or rotation is phi, if the angle of this rotation of the cross section is phi, I can always correlate this to this. Okay, I can always correlate this to this. Why? Because this is an angle or this is related to x deformation. And what would be this, friends? What would be this value? Zeta. So, you know c is related to x deformation, eta related to y deformation. Can you say zeta is related to along the length of the beam? But that is the only possibility here, right? So, I am trying to find out the deflection along the length of the beam at any point under this given m. Remember, this m is present, which will cause deflection. Because of the length of the beam, it is laterally deflecting also. So, deflection happens in two locations, one along the depth, see here, one along y, one along x, okay, and this happens along x is for the entire length of the beam. Okay. So, we are trying to plot that variation with z. Okay, friends. Having said this, let us now come to the resolving these moments. Let us say I want to find m z. Go here. I want to find m z. Can I simply say m z is mx cos phi? Can I say that? Because this is going to be also. Can I say this? M z will be mx cos phi. I am resolving it. So, mx cos phi. Since this angle is so small, can I say this as mx only? Because the value of rotation phi is very small. Then can you tell me what is m eta? What is m eta going to be? Not m zeta, m eta. M eta is going to be, because you know z and eta are normal to each other, correct? We are the cross sectional axis. If I know mz, which is cos of phi, can I say m eta is sin of phi? Because eta and z are normal cross sectional axis after deformation, right? So, I can find this. And for very small values of phi, I can simply say this is m phi, is it not? For very small value of phi, this becomes unity. For very small value of phi, this becomes phi itself. So, I can understand these two equations. Now, let me express m zeta as a differential variable along the length, because you know lateral deflection is happening along the length of the beam, is it not, along z axis. So, can I say it is sine of du by dz, du by dz. Why u by z? Okay, z is okay because along z axis, the differential is happening along the z. Why it is along u? Remember friends, if this is z axis, this is y, this is z axis, reflection is happening along x axis for the entire length of the beam. So, if you want to find any differential of this, it will be du by dz. Why minus u? This is my positive x. So, there is a shift of negative u. There is a shift of negative u. Therefore, I can say, like for example, if the beam bends as minus y, we can say minus v, right? Similarly, the beam is laterally bending. If this is my x axis, this is my u, so minus u. So, I can say it is minus du by dz, and I can call m c as mx of mc as mx of sine value. Okay, where mx is as same as m naught, mx, you know, m naught is applied about x, so mx and m naught are same. So, m naught minus du by dz. So, friends, if you want to resolve this along eta and zeta, I get mc. If you want to resolve along axis z and zeta, I get eta. Is it not? There are three axes here. Let us understand that. Z, y and x. Y and x are cross sectional axis, z is along the length. Correspondingly, for y it is eta, for x it is c, and for z it is zeta. Is it not? So, if I say eta and zeta, okay, I get mz. If I say it is z and zeta, it is z and zeta, I get m eta. Is it not? How can you say that? Simple. If I say z and y, I get mx. Is it not? This is mx. So, moment is always applied about an axis normal to these two. Moment is always applied about the axis normal to these two. By that logic, normal to these two is this. Normal to these two is this. So, normal to these two is this. Okay, that is how I done. So, therefore, I can say the general equation is ei d square y by dx square is m. Is it not? This is a general equation for theory of flexure. I am using it in a modified form here. Eiz, because the moment is about z, so Eiz, okay, and y is an axis normal, therefore d square v by ds square. Please understand here friends, this value is v, okay, therefore I am using v here, which is mz. Similarly, if we want to say I eta, then I should use u, okay. So, u of this. So, I get m zeta and m eta, which are required here. In general friends, from theory of mechanics, we can say the twisting moment is given by this equation. I change the form of this equation this way, though I am not looking at the derivation of this at this moment from the principle of structural mechanics, but I can say the moment capacity is given by this equation, whereas pi square EI by L square, friends, pi square EI by L square is something related to buckling equation, no? Whereas column buckling equation, look at Euler's theory, it is pi square EI by L square, is it not? So, pi square EI by L square will give me an idea about that it is a equation related to buckling, column buckling. So, CW and GJ, whereas GJ, we will explain these terms later, GJ, we will explain this. So, GJ indicates twisting capacity and CW is also a constant related to or a coefficient related to warping, we will talk about that. So, I am relating this equation to this, okay, and this is the equation available in the literature. Though I am not discussing the derivation of this part at this moment here, but that is how it is done. Having said this, let us look at the illustration of LTB in a cantilever beam and a simply supported beam. In a cantilever beam, the cross section which is initially vertical gets twisted. Initially vertical gets twisted, okay, and there is a lateral deflection happening, and twisting, lateral deflection. So, lateral torsional buckling. In a simply supported beam, there is a lateral bending, okay, and the cross section twists. The cross section initially vertical twists. So, there is a twisting, there is a lateral buckling, there is a lateral buckling, and there is a buckling also happening. So, LTB in simply supported beam, LTB in cantilever beam. Okay, friends. So, that is the explanation. Remember, both of them are happening under vertical load. Oh, there is no axial load. So, it is not compressed axially, it is happening on a lateral load, but the column, the beam buckles and bends laterally because of its span, the deeper web, and because of the boundary conditions. Okay. So, that is a figure of failure which happened in one of the bridges in Malaysia. So, one can see that the compression flange and the tension flange have bent, and you can say the bottom flange is completely buckled. Okay. This was the span of the beam. Because of the deeper web, it underwent large lateral deflection and the beam has twisted and failed. So, this is a typical failure of lateral torsional buckling, and it is a beam. Okay. So, beam can also buckle, right. So, what are the chances of LTB which can happen on beams? If the beam has got low flexural stiffness about the weak axis, remember friends, what are the axes of major and minor which we discussed earlier. So, if it has got low flexural stiffness is EI, you can use any nomenclature you want for the suffix of this. So, if you have got lower flexural stiffness about the weak axis, it can have LTB. If the cross section has got lower torsional stiffness, GI, can have LTB. If it has got low warping stiffness, EIW, IW, IT, IW are warping and torsional stiffness respectively. This can be computed for a given cross section from the equation of principal mechanics. We will discuss about that later. There are equations available in the literature, one can look at them. It also occurs at a very high concentrated load, and if the span is very long and restrained. When there is no lateral restraint on the span and the span is very long, it can have lateral bending, when the section is having less warping and torsional stiffness, it can buckle. Therefore, the beam can undergo lateral torsional buckling. Okay, so we will stop here, friends. So, let us write down the summary, what we have learned in this lecture. In this lecture, we learned that LTB occurs in beams. What are the conditions at which an LTB can occur? We have seen that. We have correlated the equation capacity of moment to the fundamental equation of torsional buckling, and we wrote this equation. Of course, we did not derive this equation, but we understood the nomenclature of this equation, why there is lateral, why there is torsional, and how the beam buckles. We have understood this, and we clearly understood about which axis of cross section is happening. So, if you have an axis, length of the beam, this is z axis, this is x, and this is y. When the beam buckles, z remains same, okay, but this and this axis are changing to z eta and c, and this of course is modified to zeta. So, we understood very clearly about these concepts of change of axis before and after bending and how this has happened. So, friends, please go through this lecture again for a better understanding. Refer some textbooks which derives the equation for LTB clearly. In the next lecture, we will take up a design example and show you how an equation available in international codes can be directly used to check whether the beam will undergo LTB or not. Okay, friends. Thank you very much. Have a good day. Bye. Namaste.